Hello, 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 hello. Hopefully you can see me and hear me all right. We are live back with one more live stream episode of Baji and Physics covering cosmology. Today we will talk about the Big Bang as well as sort of leading up to the formation of galaxies and at what point in the universe, in the evolution of the universe, did galaxies start to form? Because it was definitely not at the very beginning, something that we spoke about last night as well. So if you have not been to that live, then I highly recommend also playing that one because this is kind of part two of the live stream from last night. But in the meantime, while I wait for some more people to join, I'm going to put my earrings on. So there's going to be that. And do tell me how you're doing. Hopefully well. And if you're seeing this later on as a video upload, then please do leave a comment. If you see this live, please do tell us in the chat how you're doing and how everything is going. And feel free to like, share, subscribe, give us your comments, give us your chat messages, ask any questions that is pertaining to physics, astronomy, astrophysics, cosmology. For some reason, I almost said chemistry. I used to major in chemistry as well, but these lives are more focused on physics and astronomy, astrophysics, cosmology, which is the last one. Of course, cosmology is the study of the universe, especially from the Big Bang all the way up to the evolution of the universe at the current state now, and things like looking for dark energy or understanding dark energy better and understanding the expansion of the universe better, as well as something like dark matter, understanding the nature of dark matter. Those all kind of fall under cosmology, as also does understanding a large scale structure, which is also something that we touched upon last night. And in the large scale structure formation type of topics is where sort of galaxies come into play. So for a while, we didn't really talk about that because in the very, 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 very beginning of the universe, and we even set forth certain timelines of exactly what I mean by very, very beginning. It could be 300,000 years is still very close to close to the beginning of the universe, given that the universe is around 14 billion years old, or it could be 10 to the minus 43 seconds, which is also towards the beginning. So we kind of started to go into some of these specifics last night. So we will continue from there tonight after I say hi to everybody once people have joined and whatnot. Okay, so thank you very much indeed. If you're joining, I'm gonna share the live after I brush my hair here. And I am going to take a moment and share the live as well. So if you're joining, please do say hi and welcome, welcome, welcome. If you say hi in the chat, then I generally will say hi back, especially in the beginning of the live, because I kind of like to welcome everybody to the live and then get started with the topic. So this is the beginning. So if you're saying hi in the chat, this is a great time to do that. And let's see, let me share the live. Also, please do like, share, and subscribe on your end as well, because indeed I will be telling people to do that in the chat. Okay, now I will make sure. So hopefully everything is working. Is the video, audio, everything working? I hope that is the case. And we might just launch into the topic right away. It's 11:45-ish. We are live. I will say to the community post of my channel. Thank you, everybody. If you're seeing this later on as a video upload, I really do appreciate all your thoughts and comments. Any questions, comments, all of that can go in the comments of the video once it gets uploaded. And if you see this later on and we have already kind of started, well, I don't know if you'll hear me say this, but please do rewind, and then you can see the whole thing. Okay. So now, how do I... yes, okay. I see. Thank you, everybody. Please do say hi in the chat. Okay, so I think I might just get started actually. So I wanted to remind you that we are talking about this book, Astrophysics for People in a Hurry. See, this exact book. It's called Astrophysics for People in a Hurry. So if you're in a hurry today, we will be hopefully adding a lot of value to the live stream here. Because we are going to do a little bit of a book reading along with my own comments. And the author of this book is a very famous person indeed. He is Neil deGrasse Tyson. So he has a number of books. I wanted to mention that Neil deGrasse Tyson has a bunch of books, and I have like 3 of them with me right now. And this is a sort of a popular science book, so it is not going to be as detailed as some of our other lectures or other sorts of discussions that we have had. Sometimes we have even gotten into nitty-gritty of certain general relativity mathematics when we talk about cosmology. And this discussion hopefully kind of complements those types of topics and times when we covered things in more detail and also used this other book. So I wanted to also mention this book, Modern Cosmology by Scott Dodelson, is a reference book that we also use for these topics like the Big Bang Theory, evolution of the universe, expansion of the universe, the total energy density. So I'm just kind of saying some of the terms that in order to jog your memory, if you kind of catch these lives regularly, then these will be helpful. So energy density of the universe, the matter density, the total energy density, those types of things we have talked about. And we saw how 70% of the critical energy density contribution comes from dark energy, and 30% comes from the total matter density, of which only about 5% is the ordinary matter and 25% is the dark matter. So those types of things, we talked about cosmic ingredients, if you remember. So this topic is actually what we kind of talk about here as well. Hello, I see user random alphabet saying yay. Hello, user. Hello, random alphabet. Excuse me. As soon as you joined, I had to sneeze. So excuse me, and thank you so much for being here. Could you please like, share, and subscribe to this live and this channel? Thank you so much indeed. So user random alphabet, I don't know exactly who you are. Are you the... one of my... oh yes, you're B, got it. So user random alphabet is actually B, our old friend on this channel. So welcome B. Snokomui, hello Snokomui. Snokomui is saying buttercup. Hello buttercup. Hello Snokomui, how are you doing? B is saying bless you, thank you. Brady Holmes, Sherlock Holmes. I love Sherlock Holmes, so Brady Holmes, I like your last name. You are so beautiful. I could hear you talk all day. Thank you so much. Please do like, share, subscribe so that you can hear me talk all day. And in fact, you should hear me talk all day. You should play all my episodes under the live tab of this channel. There are many. I've been doing these lives now for over a year. And so we have many episodes that we have kind of talked about these exact topics, physics, astronomy, cosmology. So you are welcome to hear all of them. Just keep them playing in the background as you do your other work. You go to the bathroom, you take a shower, you go to your office. And also please tell all your coworkers, your family members, your neighbors, your sisters, brothers and everyone about this channel. Please, I appreciate it. Thank you. So B is saying the user, yes, the username used to be B. Brady Holmes is saying I will. Oh, thank you so much. You know, you guys have made my day today by being here on this live stream. Please do like, share, and subscribe. Please like the live. Can we get as many likes as there are people, which is both very small right now. Anyways, so the Neil deGrasse Tyson this is a question answer thingy thing that YouTube is asking me to start. I suppose it could be something of value maybe to people. So let me do that. There, it's done. So Neil deGrasse Tyson provides a very easy to read text on some of these same topics. So what I've been trying to say is that we have covered cosmology topics in quite a bit of detail in the past, especially if you remember certain discussions like the cosmic ingredients. Remember, we talked about the 5 cosmic ingredients of the universe, like literally all of the universe pretty much has just dark energy, dark matter, photons, neutrinos, and baryons, remember? And pretty much in the context of cosmology, baryons kind of just fell or kind of captured all the ordinary matter, and which included electrons. But technically speaking, electrons are actually not baryons, they are leptons. And in the context of more particle physics discussion, we would be more careful about that, okay? So just a few notes here about certain terminology. Sometimes the terminology of cosmology is a little bit different than the terminology of particle physics, and you might have to pay attention to what these different types of physicists mean, okay? So particle physics is where, of course, we would be more careful about naming and being specific about the particles. So let me say the same thing in another way now, which is that pretty much when it comes to cosmic ingredients, what is the universe made of? Now we know that in terms of ordinary matter, really most abundant element in the universe is hydrogen. So now hydrogen is just a proton. If you consider it as just the normal hydrogen nucleus is just a proton. Now I know that there are some isotopes of hydrogen that we can also talk about, and those are also kind of important in the evolution of the universe, but just the hydrogen is only just proton. And so that proton is made up of quarks. And we talked about it, and quarks are a fundamental type of particle. So you can see how there are some details here. So in terms of the particle physics, that would be quarks, right? It's that hydrogen nucleus is quarks. A couple different types of quarks make up our protons and neutrons. In the quark family, however, there are other quarks as well. But the most common ones that we know and love are the ones that make up the protons and neutrons of our regular elements. So in terms of ordinary matter, pretty much we are now considering basically the quarks, right? In terms of what's in the nucleus. And then if you also want to include electrons in the picture, because sometimes we include them depending on if you are at an energy scale which would support atoms, and sometimes we don't include them. For example, during Big Bang nucleosynthesis time, we wouldn't really include electrons in the same discussion as these nuclei, because, or we would, they can be in the same discussion, it's just that the nuclei and the electrons are probably not together. They're not together, okay? Because it takes a certain amount of cooling for an atom, a neutral atom, to exist. So electrons can sometimes be kind of separate from the picture when we consider nuclear physics, nucleosynthesis, Big Bang nucleosynthesis, and the conditions around the Big Bang. Okay, so these are just things that I wanted to mention so that you don't get it confused. We are not talking about, we're not always, that is, talking about neutral atoms. we do actually mean nuclei, and we might even mean more like the quarks, because those are the more fundamental particle. And depending on which energy regime you're in, we will either think of them as quarks or nuclei, or maybe even neutral atoms. But different conditions are required by each type of thing. Okay. So, so that's some more detail on the terminology, because when we start reading, you will see different authors kind of mention these things differently, and it could be a little confusing. So in terms of the cosmic ingredients, once again, so I was breaking down for you a little bit about the ordinary matter, which is just you and me, our elements that we know and love from the periodic table, the atoms, the nucleus within the atom, the protons and neutrons, in other words, and those are actually made of quarks. And in a neutral atom, you would even have electron, one or more. Then in terms of cosmology, however, you have to kind of zoom out and think of the cosmos as a whole. So in that picture, you don't just have these elements and ordinary matter that you and I are made of, but you have more of the universe to consider, and you have the cosmic ingredients. And in terms of the cosmic ingredients, we basically club all of these things that I just talked about with the ordinary matter as baryons, even though technically baryons are the just the nuclei and the different types of I would probably just lump together all the quarks under baryons. But in this discussion by Scott Dodelson, I'm just going to blame him, he also clubs together the electrons under that. So then we have ordinary matter, which cosmologists call baryons. We have photons, which is of course light. We have neutrinos, which is actually a type of lepton. And we have dark matter, and we have dark energy. So those five things. So those five things, those five cosmic ingredients actually encompass the entire universe, okay? What is in all of the universe. So not just ordinary matter, not just the elements, not just us and what we're made of, but all of the things, okay? So keep that in mind as we go forth, and also keep in mind that different authors, because we reference different writers of these topics, different scientists, and depending on what kind of terminology they like, it might be a little different. Okay. So Modern Cosmology by Scott Dodelson is quite a detailed and dense book, and we have covered these topics, some of these topics from there, especially in terms of understanding the expansion, some general relativity, dark matter and its role to some extent, the CMB, cosmic microwave background radiation, as well as we have talked about Big Bang nucleosynthesis, especially from that book, which I think is very valuable conversations that we have had in the past. Now we're looking at this book, which is a popular science book. So it's not going to be as difficult. It's not going to be as detailed or dense, but it is rather well written. And Neil deGrasse Tyson is, of course, very well known for these topics. So we are referencing this, and we will keep on going. So last night, this is part 2 of this first chapter that we are looking at. And last night we kind of talked about the Big Bang, and very shortly after the Big Bang, and I will define what that means shortly, that is. And we had not quite started on the galaxies yet, okay? So once again, after I sip this, give me a second. So once again, let me just repeat myself that let me just repeat myself that the way we see the universe now, as in the current state of the universe, with all the galaxies, with us in it, with the Milky Way, the other galaxies, lots and lots of galaxies. This is not how, this is not what we had right after the Big Bang, okay? And of course, right after is something that should be defined. But pretty much, the universe has evolved to this state that we see now, and that's taken 14 billion years. So don't think that the Big Bang directly created the galaxies, okay? Because I think that was a confusion that we saw last night with somebody who might have had trouble believing that the galaxies somehow come from the Big Bang. Well, they do, but after some other things happen first. So the galaxies, the way we are right now, the current state of the universe, once again, this is the 14 billion year old universe, okay? The universe was at one point just a little bit more than 0 seconds old. Very, very small time indeed is what we talked about last night. Like we basically talked about, let me give you the range. We talked about the interval between t equal to 0. So at the Big Bang, t equal to 0, that is the t equal to 0 when the universe got started, plus from there to t equal to minus 43 seconds. So you understand this is quite a small number. We call this the Planck era. Planck is known for his small numbers, I suppose. And this interval of time, t equal to 0 up to t equal to minus 43 seconds, is what we mentioned about last night. So we really are kind of defining out how small and how young the universe is with those with those very small numbers. So at that point, there were no galaxies. Let me just clarify once and for all. I hope you know that there were no galaxies at that point, okay? Galaxies are a much more mature state of the universe. Like think about the universe as a little baby that was born at this event called the Big Bang. And by the way, the Big Bang is most likely sort of a misnomer in the sense that it's probably neither big, because as you can see, the universe was very tiny at that time. We will talk about the length scale too. And it was probably not a bang. There was probably not an explosion. But also, I should mention that the Big Bang is a singularity. It is a mathematically, it's a singularity, at least in classical physics, in general relativity. As far as I know, I mean, if I'm wrong, please do correct me. But in general relativity or in classical physics, where we of course take into account the speed of light and relativistic nature of all that, where we consider relativity is still classical physics as opposed to quantum mechanics. That physics has sort of this, I would say, defect, where we have this singularity at the Big Bang. We don't really mathematically, not really able to explain the exact moment of the Big Bang, but shortly after, okay? And the same thing as in a singularity is what's inside a black hole as well. So there's a couple of singularities or not so comfortable mathematical positions in classical physics. And we deal with that because classical physics is still at the end of the day, or general relativity, in other words, is still at the end of the day very successful at explaining a lot of natural phenomena, and stands the test of time experimentally, and has been proven, as in predictions of general relativity have been shown experimentally and come true and things like that. So when something is so successful, we have to take it seriously, but at the same time, we have to note exactly where it kind of is falling short, okay? So at the exact moment of the Big Bang, please don't ask me exactly what is happening, but slightly just after, we can say what happens, okay? And we have a theory and things, physics and whatnot, that are working, because as you can imagine, exact t equal to 0 is hard. Like that's when literally time gets started. So we just don't have a way to really capture that in mathematics. but right after we can. So this Planck era, the interval of time from t equal to 0 up to t equal to 10 to the minus 43 seconds, which is 1/10 million trillions of a second. So, a very small fraction of a second after the beginning and before the universe grew to 10 to the minus 35 meters. So this is why I said that the Big Bang was probably not very big, because the universe was only very, very tiny at that time. So the universe came from nothing to this 10 to the minus 35 meter scale of length is what we're talking about here. So that is a 100 billion trillions of a meter across. And the German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited as the father of quantum mechanics. So because quantum mechanics has these very small numbers and things going on, and Planck is one of the fathers of quantum mechanics, basically we named this era Planck era of the universe. So as you can kind of imagine, generally speaking, now as the universe has expanded a lot, and in today's day and age, if you will, gravitation is extremely important in the universe and is obviously something that we care about, and there's a whole theory for it. It's the general theory of relativity. It describes gravitation, and it describes perfectly well when we're at this, or it describes with great success at this stage where we have a large universe and we have large scales, and all the, sort of issues that one might have with general relativity are more or less okay at those large scales. And then there's quantum mechanics, which is the physics of the very small. So see how the physics of the very small and the physics of the very large kind of, we know that they don't quite agree, and there's nothing that really puts them together. But the problem with when the universe was that small is the stuff that we use to understand the universe now kind of doesn't really work when it was that small, because the large was very small then. So there is these interesting things to consider for that scale, okay? So the clash between gravity and quantum mechanics poses no practical problem for the contemporary universe. So right now, universe, a lot of things that are disagreeing between quantum mechanics and gravity don't lead to like a complete breakdown of everything we understand in today's universe. But in the past, especially when the universe was very small, then it would have been kind of very different. And we do have to think about this issue with the two not agreeing, because the large stuff was the large did start as small. So astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. So this is the thing I was saying, where we've kind of accepted that general, or we might as well accept, because I'm not sure that there is a real solution to the issue, that the astrophysicists who care about large scales would go with general relativity. It's good when you consider large scale. And the people who care about small stuff would go with quantum mechanics. And then these two clubs of people hopefully never meet, and everything is good. But unfortunately, to the very beginning of the universe, that kind of falls apart. So astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. But in the beginning, during the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony continued to elude us, and so no known laws of physics describe with any confidence the behavior of the universe over that time. So yay, we really struggle with that Planck era, because it's it's a mystery. And things like superstring theory or a grand unification theory candidate would basically hope to achieve a unification of these things that we are talking about. And remember how when we talked about superstring theory, we talked about how the conditions where all the fundamental forces or these unifications would happen are difficult to achieve now, in fact impossible to achieve now. And that's why we are not able to, one of the reasons why we are not able to experimentally prove it out, because those conditions likely prospered during that very early time in the universe, during the Planck era, for example. And it's not like we can recreate the Planck era now. So, but at the same time, maybe there is some comfort in knowing that if such a thing, unification that is, was possible, it was hopefully probably possible during that Planck era, okay? So that's what's going on. We nonetheless expect that by the end of the Planck era, gravity wriggled loose from the other, still unified forces of nature, achieving an independent identity nicely described by our current theories. So gravitation has its own theory. It's the general theory of relativity. Gravitation is also described by Newton with his Newtonian mechanics and Newton's laws of gravity. But that is correct as an approximation. If you want things to be more accurate, then you would look to the general theory of relativity, which of course does not give us the other things, such as the particles. And for the particles, we need quantum mechanics, which is the other side of physics. Remember, the one that doesn't get along with this side. And that's why it motivated people to look for a unification or a grand unified theory, which is yet to be discovered or confirmed. Maybe there are candidates, but it's not something that's fully confirmed or proved out. Okay, so as the universe aged through 10 to the minus 35 seconds, so from 10 to the minus 43 seconds to 10 to the minus 35 seconds is the current age of the universe now, it actually continued to expand. So expansion has been incredibly important, and that kind of diluted all concentrations of energy, and what remained of the unified forces split into the electroweak and the strong nuclear forces. So we've got now electroweak theory on the one hand, and strong nuclear force on the other. Later still, the electroweak force split into the electromagnetic and the weak nuclear forces. So one more split later, we actually have electromagnetism separate from weak nuclear force, laying bare the four distinct forces we have come to know and love, with the weak force controlling radioactive decay, the strong force binding the atomic nucleus, the electromagnetic force binding molecules, and gravity binding bulk matter. So in general, we consider the four fundamental forces to be those four: gravitation, electromagnetism or magnetic force, strong nuclear force, and weak nuclear force. And we just kind of mentioned exactly what each one kind of does. Now, of course, I will mention a caveat, which is that in general theory of relativity, this word force is not really used to describe gravitation. Gravitation as a phenomenon is described as curvature of space-time. It's not regarded as a force, okay? In the geometry of general theory of relativity, which is not the geometry that we generally normally do, it's not Euclidean geometry, okay? Remember, we have to have those other geometries, geodesic, metric, all that type of stuff, and we have to treat four-dimensional space-time as the mathematics in general relativity. So not just 3D space, but 4D space-time, okay? So it's a different geometry that we follow in general relativity, in other words, and it's a different kind of math that we follow. And in that math and in that way of doing things, gravitation is not a force, okay? But in way of speaking, in way of just talking about the fundamental phenomena, forces, whatever you want to say, and especially in terms, in the under the umbrella of particle physics, we do consider, and basically we say that there are four fundamental forces: gravitation, electromagnetic force, strong nuclear force, and weak nuclear force. And there have been, as you know, there have been efforts to unify these, and they've kind of failed. And the candidate for unification at this point is superstring theory, which is impossible to experimentally show. But we believe, or there is at least this hypothesis, that maybe in the very beginning, in that Planck era, all the four forces were unified. And slowly but surely, at different levels of evolution of the universe, not biology evolution, universe evolution, the four forces have split apart, okay? As these four things that we, or the four types of forces that we see now, but they weren't always separate from each other, because remember, things change as the universe expands and as the energy levels or the energy regimes of the universe changes, okay? Because these four forces, remember, are very different in terms of the energy that is important, the length scale that is important to each one. So at some point, when the length scale was so small, you could imagine maybe everything being kind of more together-like and more unified naturally, okay? So after a trillionth of a second passes since the beginning, you started to have more things happen. So we talked about the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels. So you know what photons are, they're just light quanta. This was happening a lot. So the universe was hot enough for these photons to spontaneously convert their energy into matter-antimatter particle pairs. So pretty much the other thing that and remember from the Scott Dodelson book, which I'm also mentioning because if you've come to all the sort of associated lives on this topic, then you would have seen this one. Remember how we said that the early universe was very radiation dominated? There were just it was just this hot plasma soup, or very hot jungle soup of photons, electrons, positrons, is what we said. And that's another way to put it, is that it was radiation dominated. So it was very hot, very energetic. At that point, the universe was tiny, hot, energetic, and photons were constantly bombarding and basically converting into matter, antimatter spontaneously. And by that, it's pretty much basically a gamma ray. So a gamma ray is like a very high energy photon. So you could imagine a gamma ray basically becoming an electron-positron pair, and then immediately that electron-positron pair annihilate to become a photon again. So this type of thing, this was this gamma ray going into positron-electron, positron-electron going into gamma ray going into positron-electron, positron-electron going back to gamma ray. This type of thing was an equilibrium. This was constantly happening like crazy. And there was no chance of, there was a little bit of matter at that time because the Big Bang did give us, of course, hydrogen and a little bit of helium, very trace amounts of lithium. So because we did have a little bit of the baryon stuff, in other words, or quarks in the mix of things too. But remember that the most important dominated thing back then used to be this photons, electron-positron thingamawitch in equilibrium, okay, the hot plasma soup. So this is what was going on in those early times, okay, after a trillionth of a second had passed. So shortly before, during, so I'm kind of summarizing because we went over some of these already, but I wanted to summarize for this live, and soon we will go over to the part that we haven't covered. Okay, so shortly before, during, and after the strong and electroweak forces parted company. So at this point, basically strong and electroweak forces. So as the universe expands and the energy, it basically cools. As the universe expands and cools, you have some of these splits happening. The energy regime is changing, and so you might get a split between strong nuclear force and electroweak forces. But anyway, the universe was a seething. So it used to be the universe was a seething soup of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable their interactions. So once again, he's kind of just mentioning this hot soup, plasma soup that I was talking about. Quarks are a part of that mix for sure. Less quarks, though, I would say, I think, at those times than photons, for sure. But anyway, none of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. So then he talks about basically the particle families, which I kind of gave you a little bit of introduction to already, so I will skip over that. But basically, all of this is to say that at that point we had some quarks, because of course the Big Bang, and we have gone over this in Big Bang nucleosynthesis, the Big Bang did produce some hydrogen and very little amounts of helium and trace unmentionable amounts of lithium. So something that came from God, if you will, from the Big Bang, if you will, is hydrogen, okay, and a bit of helium. And this is what much later on, basically, the first stars and whatnot would have to work with. And all the other heavier elements that we know and love and are made of have been made in stars much later. So we're in a position, we're talking about a universe right now where there's no stars, no galaxies yet. Okay, we have not even reached that stage of the evolution of the universe yet. Okay, so, but I am wanting to mention that this hot soup, plasma soup that we're talking about from the early universe did have a bit of the quarks, because quarks are, of course, in protons and neutrons, and I'm saying that the Big Bang gave us hydrogen and helium, so those are made of that, right? Okay, so during the quark-lepton era, during the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves in spite of being collectively bound to one another. The discovery of this state of matter, a kind of quark cauldron, was reported for the first time in 2002 by a team of physicists at the Brookhaven National Laboratories in Long Island. Strong theoretical evidence suggests that an episode in the very early universe, perhaps during one of the force splits, endowed the universe with a remarkable asymmetry in which particles of matter barely outnumbered particles of antimatter. So thank goodness there was sort of a small difference in how much, because we were mentioning how the electrons, the photons were constantly spontaneously decaying into electrons, positrons, and the electrons and positrons were constantly going back into annihilate, give us photons again. So that whole reaction was sort of in equilibrium, and that was more the king of the jungle, that photon, electron, positron stuff, and quarks were much less in that cosmic soup. So, but at some point, as the universe continues to expand and cool, there developed a small difference in the number of matter versus antimatter particles. And indeed, we have more processes, like depending on which energy regime you care about, we do have more processes that make particles versus antiparticles, but it also just so happens that there was that slight asymmetry at some point, which is why we do have more particles than antiparticles. Because if we didn't, then we would not be here. Okay, so there is that as well. So now we've kind of talked about this hot soup business with the photons, electrons, positrons, a bit of quarks, right? And this way of talking about it is a much simpler way than we have kind of covered in the past. So I recommend also looking at the other lives and other books which talk about Big Bang nucleosynthesis is more in more detail. Okay, because this is basically a Big Bang nucleosynthesis conversation. Okay, so next we have now a millionth of a second has passed since the beginning. So we just covered what happened a trillionth of a second later after the Big Bang, and now we are at a millionth of a second later. Okay, still very early, but a millionth of a second old universe. Okay, so as the universe continues to evolve and expand and cool down, things change in the universe. Okay, so this tepid universe, a millionth of a second old universe, was no longer hot enough or dense enough to cook quarks. So pretty much all these quarks grabbed dance partners, creating a permanent new family of heavy particles called hadrons. So, you know, this Greek word hadros meaning thick, that quark to hadron transition soon resulted in the emergence of protons and neutrons, as well as other less familiar heavy particles, all composed of various combinations of quark species. So this quark business, when we say that the Big Bang gave us hydrogen and helium, really, depending on when you talk about and the energy regime, it would just be quarks, right? But then as the universe is at its sort of a millionth of a second into its life of evolution, we do have a bit of cooling, enough to make the quarks grab each other in a way to make protons and neutrons now, okay? So in Switzerland, we have the Large Hadron Collider, and you know, there are questions that we ask in particle physics where we try to probe physics that would only happen at very extreme conditions. And that's why they made that collider, for example, because again, it's kind of difficult to recreate and understand the physics of the very early universe because we don't have those conditions anymore. We might have to create something like them in an artificial way. Okay, so the slight matter-antimatter asymmetry afflicting the quark-lepton soup now passed to the hadrons, but with extraordinary consequences. As the universe continued to cool, the amount of energy available for the spontaneous creation of basic particles dropped. So because of expansion, universe is expanding as well as cooling, and the amount of energy available for the spontaneous creation of basic particles is dropping. So because if you have a lot of energy, then the photons, remember, would give you the electron plus positron pair. But if you have a cooling universe, then shenanigans like that, where there's too much energy and oh my gosh, I'm decaying into something, will happen a bit less, okay? So during the hadron era, ambient photons could no longer invoke E equals mc squared to manufacture quark-anti-quark pairs. Not only that, the photons that emerged from all the remaining annihilations lost energy to the ever-expanding universe, because one of the biggest things, of course, we get from the Big Bang Theory is an expanding universe, which also matches evidence, and an ever-expanding universe is losing energy. So once again, the photons that emerged from all the remaining annihilations lost energy to the ever-expanding universe, dropping below the threshold required to create hadron-anti-hadron pairs. So this whole situation of photons being like, oh my gosh, we will break into things and make quark-anti-quark or whatever, is happening less now. For every billion annihilations leaving a billion photons in their wake, a single hadron survived. Those loners would get to have all the fun, serving as the ultimate source of matter to create galaxies, stars, planets, and petunias. So basically, once again, this situation of the Big Bang nucleosynthesis, meaning we got a bit of matter, as in quarks, as in another way to put it would be hydrogen and helium, but really it's just the quarks, and quarks can annihilate with their anti-quarks and make photons, and photons can, when very angry and hot, make quark, anti-quark, electron, positron, all that stuff. But you have to remember that with a cooling universe, because of an ever expanding universe, there's less and less energy available for the photons to make a lot of these quark, anti-quark. So now, within a millionth of a second into the Big Bang created universe, we're already seeing a lot more photons than we see quarks. And so that's why we say, again, that early universe was radiation dominated. Photons are king of the jungle. Like, photons were much, much more and much, much more important than, for example, quarks or ordinary matter. But later on, much later, those few quarks that are really available at this point will go on to make galaxies and everything like us, everything that we know and love in terms of matter. So a lot can happen starting from very small, especially very small amounts, right? So very small amounts of quarks in an ever-expanding cooling universe later on goes on to make all of the galaxies, okay? We're not at the galaxies yet. We've just finished talking about a millionth of a second after the Big Bang, okay? So no galaxies, no nothing like that, no galaxies. So what is the universe at that point? Mainly photons, electrons, positrons. Very small amounts of quarks, okay? So this falls under Big Bang nucleosynthesis. Please Google it, study it from a cosmology book, go to a class about it to get the full picture of this. But this is what's going on. This is the stage of the universe we're talking about right now, okay? Very young universe, millionth of a second old. Big Bang nucleosynthesis. King of the jungle, photons. Most things are photons, electrons, positrons, and very few amounts of quarks, okay? No galaxies. But it's incredibly fascinating that these few quarks later on, much later, will make the galaxies, okay? And us. So, so like he says, ultimate source of matter. The loners, as in the quarks, would get to have all the fun, serving as the ultimate source of matter to create galaxies, stars, planets, and petunias. Everything comes from those quarks, because all the early galaxies, everything came from these quarks, and those galaxies have stars, and the stars have been born and died and spewed their matter out to make us, okay? So without the 1,000,000,001 to a billion imbalance between matter and antimatter, all mass in the universe would have self-annihilated, leaving a cosmos made of photons and nothing else. So if you basically had the same number of particles and antiparticles, they could annihilate to make photons and nothing else. Because if you then stop being hot enough for photons to be crazy and make particle, antiparticle, then those processes are the photons going into particles, or sorry, the photons going into matter particles, because a photon itself is a particle. It's a light particle, it's a boson particle, but basically photons making, say, quark, anti-quark, electron, positron. If that is kind of winding down as the universe gets older, and by old, I really don't mean very old, like even within a millionth of a second, or millions of, like within a few millionth of a second, at that point already, if that process is winding down, and some of those annihilate to make photons, and there wasn't a difference in the number of particles versus antiparticles, then everything could potentially just be photons, and that's it. The universe could just be photons, and that's it. And we wouldn't be here talking about a universe which has quarks, because we are made of quarks. Okay, we are made of elements which are made of nuclei, which are made of quarks. So yeah, okay. So now we come to 1 second has passed after the Big Bang. Okay, 1 second has passed after the Big Bang. Sorry, to send one text. 1 second has passed after the Big Bang. So still a very young universe, I would say, but things have already changed a lot. Okay, the universe has grown to a few light years across. So look at this. When we say ever expanding universe, no joke, ever expanding universe, because already within a second of time, the universe has grown to a few light years across, about the distance from the sun to its closest neighboring stars. At 1 billion degrees, it's still plenty hot and still able to cook electrons, which, along with their positron counterparts, continue to pop in and out of existence. Because, you know, the photons can go into electron, positron, annihilate to go into photons. But in the ever-expanding, ever-cooling universe, their days, seconds really, are numbered. So what was true for quarks and true for hadrons had become true for electrons. Eventually, only 1 electron in 1 billion survives. So most electron positron will make photons, but there will be say maybe a few that don't annihilate, right? And the rest will annihilate with positrons, their antimatter sidekicks, and in a sea of photons. So once again, you can see even at this time, which is basically a second after the Big Bang, photons are still king of the jungle. It's definitely still too hot and energetic to basically make a lot of ordinary matter particles like electrons and quarks, because things are annihilating with their partners, with their antimatter partners, and becoming more photons, and not as many not as many photons are maybe doing the other way around process. And for like 1 billion annihilations, maybe there is one that's like not annihilating to make photons, and then that one is a loner that gets to survive this situation and continues to be an electron, or continues to be a quark. Okay, so right about now, 1 electron for every proton has been frozen into existence. As the cosmos continues to cool, dropping below 100 million degrees, protons fuse with other protons as well as with neutrons, forming atomic nuclei and hatching a universe in which 90% of these nuclei are hydrogen and 10% are helium. So I told you how the Big Bang gave us... why I'm saying this is because, you know, we consider the Big Bang to be the beginning, and this is just after the beginning. But basically this situation is when about a second of time has passed since the beginning of the universe, is when we're basically starting to make these nuclei. Okay, so before this, it's just a quarks, it's just a hot soup of plasma, and the level of the particle is it's quarks. But once you have this level of cooling now, after about a second, then you start to make the nuclei. Okay, now 2 minutes have now passed since the beginning. So what happens after 2 minutes? For another 380,000. So in the first 2 minutes, we basically got those nuclei, the hydrogen nuclei and the helium nuclei, where 90% are hydrogen and 10% are helium and very trace amounts of lithium. So that's all we got to work with, by the way. So in the first 2 minutes, we got that big. So that this all falls under Big Bang nucleosynthesis. We get this, and this is what we have to work with later on to make the galaxies. But we're not there yet. So what happens between the 2 minutes and the next 380,000 years? Not actually much will be happening to our particle soup. Throughout these millennia, so 380,000 years, right? A lot of years. Throughout these millennia, the temperature remains hot enough for electrons to roam free among the photons, batting them to and fro as they interact with one another. But this freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin. So this whole situation of particle soup still pretty radiation dominated, still lots of photons, but we do have a few loner electrons and quarks and whatnot. But throughout these thousands of years, up to the 380,000 years, temperature remains hot enough for electrons to roam free among the photons, batting them to and fro as they interact with one another. But as soon as the temperature drops further, there's a point at which this freedom comes to an abrupt end. Universe has expanded more and cooled more. So at around as soon as the temperature is below 3,000 degrees Kelvin, all the free electrons combine with nuclei. So this is the point at which you can start to get the neutral atoms. So remember how I said that neutral atoms is not a thing depending on the conditions you're in. So if the conditions are too hot, too energetic, then you would not get neutral atoms. You would just get the nuclei, maybe not even nuclei, maybe just quarks in the soup. But at this point, once you go below 3,000 Kelvin, you start to get some neutral atoms. The marriage leaves behind a ubiquitous bath of visible light. So these are the hanging out, these are photons that are hanging out now. So the marriage of so once again, let me read this sentence because it's very, very nice. The freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin, about half the temperature of the sun's surface. So see, it's cooler than the sun in some ways, and all the free electrons combine with nuclei. So now we get neutral atoms. The marriage of the electrons with the nuclei to make the atoms leave behind a ubiquitous bath of visible light, forever imprinting the sky with a record of where all the matter was in that moment, and completing the formation of particles and atoms in the primordial universe. So pretty much this completion of the formation of particles and atoms in the primordial universe takes place now when the temperature, after further expansion of the universe, of this ever-expanding universe, once the temperature drops below a certain amount, you actually get neutral atoms. And then the photons that are given off at that time, the visible light that's given off at that time, basically forever imprints the sky. Like the photons that are hanging out from that period, we can actually measure even now. So there is that. So for the first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. Nearly 100 billion of them formed, each containing hundreds of billions of stars that undergo thermonuclear fusion in their cores. Those stars with more than about 10 times the mass of the sun achieve sufficient pressure and temperature. So pretty much once you have these neutral atoms, and that's what we have to work with in the primordial universe. Now we're at billions of years in. So it's not for billions of years where we would even consider making any galaxies in the universe. Okay, so once again, the the universe has continued to cool, expand as matter gravitated into the massive concentrations we call galaxies. So, because remember we talked about the smooth universe, this topic that we just left, the one where photons were given off, neutral atoms were formed, and the photons from that time is still hanging out, and we can pick up on them, we can measure them. It's called the cosmic microwave background radiation, etc., etc. That was a very smooth picture of the early universe. But guess what? There are some certain fluctuations in that map and certain spots of overdensities where gravitation kind of won in certain spots. It's very little. The smoothness is very perfect. It's very smooth to a large extent, but there are these sort of higher order perturbations, and because of that, because of those overdensities, which is a whole topic of its own, which by the way we have also talked about. We've talked about the CMB. Led to galaxies. But basically, as you can imagine, if matter had never clumped in certain spots of the universe, then we would not get galaxies, right? So if matter is clumping, that means that there is spots of overdensity and fluctuations to the smooth universe. So for the so once again, this distribution of matter, by the way, another thing to keep in mind is this topic that I just now talked about, understanding how matter clumped, understanding why matter clumped, understanding why there are even these spots of overdensities, understanding the fluctuations in the CMB is a very important topic, and what could be the role of dark matter in that, etc., leads to us understanding large scale structure. So also, as you can imagine, we have this map of the universe from when it was 380,000 years old. And of course, there were no galaxies at that time. But now we have we have some map of the universe, and we have a distribution of matter that we can observe to some extent, at least in the universe. And we have galaxies. It's almost like a before and after picture of the universe that we have access to. It's like the CMB is the before picture, or the baby picture of the universe, and the now is the after picture of the universe. And many people are interested and curious in understanding how things have evolved between those before and after, and what led to what. Like how did, like we see this before picture, which is the smooth universe, and note that there are tiny little fluctuations, but we want to ask why those fluctuations exist, and how did they further develop to give us galaxies, okay? And what is the role, if any, of dark matter in that? And that is an extremely important and very exciting question. So things like that, okay? These are the nitty-gritties where actually the real interesting details are. So keep that in mind. By the way, can we get some likes and subscribes, please? That would be most amazing. Some likes and subscribes. Could you please like, share, and subscribe? It's been so quiet today, but I actually did someone ask a question just now? Oh, wait. I did not see your comments. Hello, Mr. Drew. For all this time that I've been speaking, I completely missed all of y'all's comments. The last comment that I see hanging out, sort of like the CMB photons, is Brady Holmes from a while ago. After that, I was thinking, gosh, it's been so quiet. But YouTube did something. I don't even know if my live is working. Do you see my face and do you see the video and audio of this live? But now that I see it on my other phone, I can see the comments, guys. Thank you so much, everybody, for being here. B is saying, I don't know why, but Neil deGrasse Tyson rubs me the wrong way. Well, I hope he's not rubbing you in any way. User is saying, I'm 3/4 Mirana Fermion. Steven! Hello, Steven! Oh my gosh! I'm so sorry. I didn't see people until now. Steven is saying, hi, friend. Hi, all. Hello, Steven, my friend. How are you? I expect my book to be out by the end of this week. How are you, B? Combat Sports says, oh, funny. It's been a while and I'm at Boston. I almost hear you from my window. Hello, Combat Sports. I'm sorry I didn't see you. I hope you're still here. Steven says, I've been to Boston. Anyone else interested in the Comet 3i Atlas? Big Frank is saying hi, Merry Christmas. Hello, Big Frank, 1010. How are you? How are you, my friend? Merry Christmas. What are you talking about? So tonight we're talking about the same thing as last night. This is part 2 of last night. The universe stuff, you know, early universe and its evolution, the Big Bang, and we're just about to talk about galaxies and the formation of galaxies, and I hope that it's clear about the large-scale structure stuff that I just mentioned. What is dark matter? I can see your beautiful face, says Mr. Drew. I will not be ignored. Hello, Mr. Drew. Did you like the live? Can you please like it? I see the #1 top fan is B. Thank you. Mr. Drew is #2. #3 is Steven. Brady Holmes is 4. Big Frank is 5. Hey, can you guys like the freaking gosh darned live, please? Can we get 10 likes? What nonsense is this? What is this nonsense? I don't see any likes. I couldn't see the comments. I couldn't see the people. This is just ridiculous. This has been a most disappointing exercise, but also I kind of liked the peace and quiet to talk about things. So I don't know what to say. Can someone do a super chat? Can you increase the engagement of this gosh darned live stream, please? We are live. So we will now talk about billions and billions later, billions and billions of years later. I don't understand this. I don't understand. You gotta dance break in between your talks. Oh, thank you, Mr. Drew, for this novel idea. I don't understand if I'm even seeing all the comments or not, but here we go. It's okay. Kitty cats have run down. Okay, we will keep going for at least a few more minutes because I want to touch upon the things with the things. Okay, thank you everybody for being here. Please do like, share, and subscribe. I'm asking. Okay. So for the first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. So this situation of matter gravitating towards each other and clumping is because of gravitation winning in certain spots of the universe to make those galaxies, right? And if there were not fluctuations, like if everything was so homogeneous and what's the word, smooth and isotropic, as we largely see the CMB as, which is the early universe, or the signature of the early universe, then there would be no clumping. Matter is clumping, right? There would be no clumping, and there would be nothing getting close to other things. And I mean thing quite literally, as in matter, right? No matter would be clumping to give us the beginnings of galaxies. This would not be happening, right? If everything was very smooth, very isotropic, very homogeneous, then we would not get this type of thing happening. But the fact is that matter gravitated into the massive concentrations that we call galaxies, which started off with those spots of overdensity, okay? Nearly 100 billion of them formed. So I think yesterday somebody asked how many galaxies there are. There are many, and I'm not sure that I know exactly how many, but nearly 100 billion of them formed, each containing at this point, that is within the first billion years of the universe, nearly 100 billion of them formed, each containing hundreds of billions of stars that undergo thermonuclear fusion in their cores. So this is where we will see that all of the heavier elements, that is heavier than helium, have formed in these stars, for example. That will be part of these galaxies. So first of all, 100 billion or so galaxies have formed due to matter gravitating towards each other, which is not a trivial phenomena. It comes from those fluctuations in the smooth universe, which is itself a topic of study. But then within the galaxies, we also have stars, which are these objects where that undergo thermonuclear fusion. They all have a nuclear reactor in their bellies. And we can go into lots of detail about stars, and we have in past live streams. There can be stars of all these different sizes, for example, in terms of mass. And depending on the mass of the star, they will have different fates, actually, as in what happens to that star, what kind of death it suffers. It depends on the mass of the star. So we can go into a lot of detail about stars, but pretty much at this point, we know that 100 billion of these galaxies formed. They have stars, which are thermonuclear fusion, reactors pretty much in their bellies. Those stars with more than about 10 times. So again, once again, depending on the mass of the star, right? So the stars with more than about 10 times the mass of the sun achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen. So not just hydrogen, like for example, our sun is taking hydrogen and turning that into helium. Our sun, that is a pretty low mass star in that sense, and it primarily just makes helium. Okay, but if you get a star with a mass that is a lot more than the mass of the sun, and we say, we compare things to our sun a lot because that's our star. We're part of that star's system, solar system, in other words. And so we often end up thinking about other stars or other objects in terms of our sun, comparing the mass or the size or something to our sun. But, there are stars which are quite different from our sun with much, much more mass. And say, if it has more than about 10 times the mass of the sun, then those stars those stars with more than about 10 times the mass of the sun achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen. And we can go into the details of exactly how, like, what is the nuclear physics that happens within these stars to make these heavier elements, but just know that they can make more. So including those that compose planets and whatever life may thrive upon them. So all of the elements, literally all of the elements heavier than hydrogen and helium are made in stars, okay? Now it just depends which element, say, you're interested in. More than likely, for sure, they're all made in stars. The only elements that we got from that first about a second of the universe after the Big Bang, or the start of the universe, is, remember, just hydrogen and helium, and that too mostly hydrogen, 90% hydrogen and about 10% helium, and very trace amounts of lithium actually as well. But if you want elements heavier than that, and for example, us, what we're made of, carbon, oxygen, nitrogen, iron, all these things are made in stars, okay? And depending on the star, you will get different processes that support the manufacturing of heavier elements. And depending on the mass of the star, you would get more and more types of elements, okay? And more numbers of elements. These elements would be stunningly useless were they to remain where they formed. So, stars are making these elements, which is a great thing. But you also have to remember that it's also the way in which stars die explosively, right? Stars die, and that death of the star is called a supernova. It's also incredibly important for the stars to die in an explosive manner, in a way which will spew a lot of the material that the star has made during its lifetime into the interstellar spaces, which leads to having gas and, gaseous nebula and things like that out, just hanging out in space after being spewed from this star, just goes everywhere. Because without that, we would not be here, for sure. Like the first populations of stars could do this thermonuclear reaction stuff, the nuclear reactor in its belly, doing all these elements, making all the elements, and then those, making even more elements depending on the mass, etc. That could have happened all day long. But if the material is not spewed, and then even more metal-rich gaseous nebula goes on to make the next generation of stars, then we would not be here, because we are actually from a pretty metal-rich nebula ourselves that condensated eventually to make our sun and our planets. So, and that type of nebula that we are from would not be hanging out in, for example, this part of the galaxy, in our own galaxy where we are, Milky Way galaxy, if some star had not lived and died and spewed its material out, or at least some of its material out, okay? So these elements would be stunningly useless were they to remain where they formed. But high mass stars fortuitously explode. So it is a sort of kindness of the star that it explodes, scattering their chemically enriched guts throughout the galaxy. So whenever a star dies, it has a very spectacular, depending on especially the high mass stars, there are also different classes of supernovae, but the highest mass stars will have a spectacular supernova, which can actually shed a lot of material during the core collapse and the supernova process, and kind of blow off the outer layers of it, and even a lot of the material that it has made over the years into the interstellar medium and space. Into space. Basically, all of these elements go out into space around the star and all throughout the galaxy. And if that didn't happen, then we would not have metal enriched gaseous nebula or gas clouds floating around, eventually condensating to make our sun and us. Okay? So, after 9 billion years of such enrichment in an undistinguished part of the universe, the outskirts of the Virgo supercluster, that's where we are, in an undistinguished galaxy, the Milky Way, in an undistinguished region of the Milky Way, the Orion Arm. So, because remember, we talked about the Milky Way's spiral arms, and we are in one of them, Orion Arm, an undistinguished star, the sun was born. So, once again, 9 billion years of enrichment, stars living and dying, and then spewing material into the space around them, into the, throughout the galaxy, etc., etc. This type of thing has happened over time, for a long time. And then here we are, undistinguished part of the universe, which is the outskirts of the Virgo cluster. This is just defining our neighborhood here, kind of like our address. Where can we be found in the universe? In an undistinguished galaxy, which is our Milky Way galaxy, in an undistinguished region of that galaxy, Orion Arm, an undistinguished star, the sun was formed because of some gas cloud that was generally hanging out, kind of condensated into the sun and its planets, where most of the, just a fun fact, most of the angular momentum of that nebula went into the planets, and most of the mass, over like 99% of the mass, went to the sun. Okay, so this is how we come to have the solar system, which is pretty interesting. And we've talked about that as well, this exact thing, when we talked about the planets. I have a whole playlist on that you're welcome to check out. Okay. The gas cloud from which the sun formed contained a sufficient supply of heavy elements to coalesce and spawn a complex inventory of orbiting objects that includes several rocky and gaseous planets, hundreds of thousands of asteroids, and billions of comets. So those are the makeup of our solar system. For the first several 100 million years, large quantities of leftover debris in wayward orbits would accrete onto larger bodies. This occurred in the form of high-speed, high-energy impacts. So we talked about impact craters when we talked about the planets. It's very important. See how our moon has craters and we don't? It's because the moon, for example, is geologically kind of dead and has an older surface, and we, Earth, is geologically more active and have paved over a lot of our craters, but we too were impacted a lot. So don't think that the Earth was missed when we were getting hit a lot during the era of being hit by planetesimals, is the word for like all this debris in the solar system. We were hit a lot too. Okay, we were also cratered, but the thing is that we also have volcanoes. We are a different kind of beast in terms of an object. So the Earth has paved over a lot of its craters. So even though cratering happened, we don't show as much as, for example, the moon, which is an older surface. Okay, so I mean, it has, of course, some similarities with Earth as well, because we think it is partly, it is kind of like a piece of Earth. But anyways, this occurred in the form of high-speed, high-energy impacts, which rendered molten the surfaces of the rocky planets, preventing the formation of complex molecules. Ooh. Oh, that's interesting. I didn't think of that. So for the first several 100 million years, large quantities of leftover debris in wayward orbits would accrete onto larger bodies. This occurred in the form of high-speed, high-energy impacts, which rendered molten the surfaces. The surfaces. Got it. The surfaces didn't have. That's right. Our surfaces didn't have those molecules, which rendered molten the surfaces of the rocky planets, preventing the formation of complex molecules. As less and less accretable matter remained in the solar system. So this is when there's a lot of debris just flying around constantly. This is way before our time. And pretty much things have cleaned up since then. So as less and less accretable matter remained in the solar system, planet surfaces began to cool. So in the beginning, it would have been all this debris clashing and cratering us and impacting us would have caused chaos and moltenness and blah blah blah. But slowly but surely, the planets have cooled as well, especially us, the rocky planets, because we're smaller. The one we call Earth formed in a kind of a Goldilocks zone around the sun. So we are one of the rocky planets, Earth. The rocky planets are, of course, just Mercury, Venus, Earth, and Mars. We have talked about, once again, we've talked about the planets in a lot of detail. So we're lucky, very lucky, because we are on Earth. And Earth is one of the rocky planets, which is also in a very perfect zone around the sun, where oceans remain largely in liquid form. Had Earth been much closer to the sun, the oceans would have evaporated. So not having liquid oceans or liquid water oceans is a really big bummer, because you will see, hopefully he talks about it, but we have talked about it in the past about how terribly unlucky Venus is in terms of, not being able to clean up its atmosphere, but because the oceans actually have a role in that. So, had Earth been much closer to the sun, the oceans would have evaporated. Had Earth been much farther away, the oceans would have frozen. In either case, life as we know it would not have evolved. Within the chemically rich liquid oceans, by a mechanism yet to be discovered, organic molecules transitioned to self-replicating life. But also what, I'm not sure if he's going to mention this or not, I want to say it, the life part is there, but also liquid ocean actually helped to clean up a lot of the atmosphere. So let me now briefly look at this other book because it has a good explanation of that. So hang tight. So basically, there is a little explanation that I want to give to you. Yes, right here. So let's talk about Venus really quickly before we continue to talk about Earth. So Venus is very similar in size to Earth. Venus is actually our twin, not Mars. Also, Venus is closer to the Earth than Mars. But notice how nobody is talking about going to Venus and everyone is talking about going to Mars. Well, we can talk about Mars too, maybe another day. We have talked about Mars a lot. But pretty much the unfortunate thing about Venus is that its atmosphere is very poisonous and it's very hot there. I mean, it's closer to the sun. So it's closer to the sun. So it's very hot and its atmosphere is very poisonous. So let's talk about it. So Venus is too hot for liquid water to exist. Mars, on average, is too cool for liquid water to exist. It was only in the warmest, highest pressure regions of Mars that liquid water flowed in the past. So by the way, Mars did have liquid water at some point, so we think that there could have been life on Mars. That's a side note. However, the average temperature and pressure on Earth has been close to the triple point for much of the planet's history, meaning that gaseous, liquid, and solid water could all exist in significant quantities near the Earth's surface. Astronomers, thinking back to the stories of their childhood, sometimes refer to the Goldilocks effect. Venus is too hot for liquid water, Mars is too old, or Mars is too cold, but the Earth is just right. So that's the liquid water part. But wait a minute, it's still not Here it is. Here it is. The thing that I wanted to also say. So part of the issue with Venus is it's too hot for liquid water. So the liquid water being not there is bad because, life, it seems to support life. But the other thing I wanted to mention, which people don't talk about enough, is that the other issue with Venus, like you can't breathe on Venus, right? So unfortunate. So even though Venus and Earth are so similar, Venus has a very poisonous atmosphere, right? And that's a huge issue. So, an intriguing question is why the atmospheres of Venus and Earth are so different from each other. Venus and the Earth are nearly twins in radius and mass. So, not just in radius, but also mass. So, very similar to planets, right? Why then does Venus have nearly 100 times as much atmospheric pressure as the Earth? The key difference between the two planets in this context is that the Earth has liquid water covering most of its surface. So this is where another very important role of the liquid water on Earth comes into play, which I want to tell you for the n-1th time because I love it. I just love this about Earth and Venus. So the key difference between the two planets in this context is that the Earth has liquid water covering most of its surface. Carbon dioxide dissolves in water where it forms, among other compounds, negatively charged bicarbonate ions. So this is where chemistry plays a very big role. So carbon dioxide plus H2O or water is H plus HCO3 minus. Okay? The bicarbonate ions. So the bicarbonate ion HCO3 minus. This is going to be so important. The bicarbonate ions combine readily with any calcium ions dissolved in the water. So that Ca2 plus, so calcium has the 2 plus charge, ions of calcium, that is Ca2 plus 2 HCO3 minus. So two of those bicarbonate ions together will give you CO2 plus H2O plus CaCO3. Isn't that great? CaCO3, calcium carbonate, is basically a remarkable compound. Why? Because it's poorly soluble in water, so it precipitates out to the ocean floor. Limestone, which occurs in abundance near the Earth's surface, is a sedimentary rock that consists largely of calcium carbonate. So making this calcium carbonate was very important. Literally, the liquid water, our oceans are so important in cleaning up our atmosphere, because if you're not catching the carbon dioxide from the atmosphere and combining it with the liquid water and turning it into the bicarbonate ions, and then the bicarbonates go on to chemically combine with calcium to make calcium carbonate, which is then converted to basically sedimentary rock at the bottom of the ocean floor or limestone, that is an active process that cleaned up our atmosphere, which does not happen in Venus, because poor Venus is too close to the sun and it does not support water to exist in liquid form there. So Venus, unfortunately, still has a very poisonous and thick atmosphere. So even if we found a way to it's too hot there, but also the atmosphere is not friendly, okay? So limestone, which occurs in abundance near the Earth's surface, is a sedimentary rock. Just said that since Venus is too hot for liquid water to exist, it lacks this mechanism for removing carbon dioxide from the atmosphere and locking it up inside rocks. Literally, our oceans has helped us to clean up our atmosphere, catch the carbon dioxide, and turn it into rocks. Isn't that so cool about Earth? So yes, life is supported by liquid water, but also this process is supported by liquid water. The conversion of carbon dioxide, bad, to rocks, good, on Earth, which we absolutely need to do in order to breathe here. Goodness gracious. Also, plants have helped too, right? There's that too. So if you could somehow remove the carbon dioxide from the Venusian atmosphere, so if we could go to Venus and clean up its atmosphere, the remaining atmosphere, consisting mostly of nitrogen, would resemble the atmosphere of Earth prior to the emergence of photosynthesis. So Earth has done the liquid water thing where it grabs carbon dioxide and converts it into rock. Plus, then Earth has supported the liquid water and everything else. I mean, I'm not a life expert, but we also have plants which also convert carbon dioxide, right? And so our atmosphere, so in other words, Earth's atmosphere has evolved. Earth's atmosphere wasn't always clean and breathable, okay? We have to thank our oceans, we have to thank liquid water for helping to clean up the atmosphere. And then also we have to thank the plants, because pretty much after doing all this, now we see the Earth the way it is. Now we see the breathable air, whereas the Venusian atmosphere did not get the help from the oceans because it cannot support oceans. It's too hot for that. And also doesn't have plants. So the pre-photosynthesis atmosphere of Earth would pretty much resemble the Venusian atmosphere if it weren't for our oceans. So we would have been a lot more like Venus, and we are like Venus. So that's why Venus is my favorite planet. So, I mean, other than Earth. Basically, Venus and us, we're like gonna be like twin, but it's too hot for liquid water. Unfortunate. So conversely, if you could unlock all the carbon dioxide presently contained in the Earth's limestone, the Earth's atmosphere would strongly resemble that of Venus. So, oh my gosh, isn't that crazy fascinating? Isn't that so fascinating? Oh my gosh. I love it. We would be just like Venus. If we, not that I wish a poisonous atmosphere to us, but if we unlocked all the carbon dioxide in the limestone in the ocean to the atmosphere, we would be a lot like the Venusian atmosphere, which you cannot breathe. So let's not do that, guys. Let's not do that. So anyway, plus the liquid water also helps life, but ask a biologist about the details of that. But let's see what Neil deGrasse is saying. So in either case, life as we know it would not have evolved if we didn't have liquid water. Within the chemically rich liquid oceans, by a mechanism yet to be discovered, organic molecules transitioned to self-replicating life. So this whole situation of self-replication and making cells and becoming more cells and becoming living organisms, which I'm not an expert at all, is what happened here on Earth. Dominant in this primordial soup were simple anaerobic bacteria, life that thrives in oxygen-empty environments but excretes chemically potent oxygen as one of its byproducts. These early single-celled organisms unwittingly transformed Earth's carbon dioxide-rich atmosphere into one with sufficient oxygen to allow aerobic organisms to emerge and dominate the oceans and land. So some of the first life forms might have been these, I think they are these anaerobic things. We got help from the oceans, but we also got help from these anaerobic organisms, which further cleaned up the atmosphere and made way for aerobic organisms who like to breathe air and get oxygen from that air. These same oxygen atoms, normally found in pairs, O2, also combined in threes to form O3 or ozone in the upper atmosphere, which serves as a shield that protects Earth's surface from most of the sun's molecule hostile ultraviolet photons. So we don't want the sun's ultraviolet photons to disturb us too much, because it can be destructive to what makes up life, okay? So wear that sunscreen. Everywhere. Wear that sunscreen everywhere, because the sun's ultraviolet lights are destructive to life, okay? We owe the remarkable diversity of life on Earth, and we presume elsewhere in the universe, to the cosmic abundance of carbon and the countless number of simple and complex molecules that contain it. There's no doubt about it. More varieties of carbon-based molecules exist than all other kinds of molecules combined. But life is fragile. Earth's occasional encounters with large wayward comets and asteroids, a formerly common event, because I was telling you about in a different era when the impacting and getting hit was quite common, wreaks intermittent havoc upon our ecosystem. So it can mess up our lives because we can get hit. A mere 65 million years ago, so that's not very long ago, because that is only 2% of the Earth's past, because the Earth is around 4 billion years old. A 10 trillion, I was just thinking about the timings, 9 billion years and then 4, yeah, okay. A 10 trillion ton asteroid hit what is now the Yucatan Peninsula. Wow, guys, Yucatan Peninsula. So only about 65 million years ago, a 10 trillion ton asteroid hit what is now the Yucatan Peninsula and obliterated more than 70% of Earth's flora and fauna. What a bummer. I mean, as in, well, so we used to get impacted a lot, in other words, okay? We would have these things hit us all the time, including all the famous outsized dinosaurs extinction. So we were, the life on Earth has gone through certain extinctions because of these things. This ecological catastrophe enabled our mammal ancestors to fill freshly vacant niches rather than continue to serve as hors d'oeuvres for T-Rex. So we used to be appetizers, I suppose, for the dinosaurs. Not us, but like, you know, our ancestors. But then those dinosaurs died. Sad for them. Good for us. One big-brained branch of these mammals, that which we call primates, evolved a genus and species, Homo sapiens, with sufficient intelligence to invent methods and tools of science and to deduce the origin and evolution of the universe. So we are those primates that have a bigger brains or something. What happened before all this? What happened before the beginning? So next question of this first chapter is, well, we're here, but what about before the beginning? Is there any such thing? Is there, I know that Stephen Hawking basically says that the beginning of the universe is that t equal to 0 is the Big Bang happening, the universe getting started, and there's nothing before. The concept of time is meaningless for before then. But let's see what Neil deGrasse has to say. Astrophysicists have no idea, or rather our most creative ideas have little or no grounding in experimental science as far as the before part, okay? As far as all the Big Bang stuff that we've been talking about, we do actually have evidence, so I don't want to confuse people. In response, some religious people assert with a tinge of righteousness that something must have started it all, a force greater than all others, a source from which everything issues, a prime mover. In the mind of such a person, that something is of course God, but what if the universe was always there, in a state or condition we have yet to identify? A multiverse, for instance, that continually births universes. Or what if the universe just popped into existence from nothing? That could be true. Like maybe the universe just popped into existence from nothing. Or what if everything we know and love were just a computer simulation rendered for entertainment by a super intelligent alien species? This is also probably somebody's idea, okay? These philosophically fun ideas usually satisfy nobody. So this type of discussion of exactly what happened before, if there is a before, depending on who you ask, I think, like, for example, I was mentioning Stephen Hawking would say that there is no before that we would know of. We understand the universe we're in and that we try to understand T equals 0 is when this universe got started. So there is nothing, there's no T before that. It starts at 0, okay? There's these, so, you know, these are philosophical, fun ideas. This is not to be confused with the evidence that we do have and see about the universe starting at the Big Bang. But anyways, nonetheless, they remind us that ignorance is the natural state of mind for a research scientist. People who believe they are ignorant of nothing have neither looked for nor stumbled upon the boundary between what is known and unknown in the universe. There's a lot that we don't know, we agree. What we do know, and what we can assert without further hesitation, is that the universe had a beginning. The universe continues to evolve. And yes, every one of our body's atoms is traceable to the Big Bang and to the thermonuclear furnaces within high mass stars that exploded more than 5 billion years ago. Why more than 5 billion years ago? Because the Earth is over 4 billion years old, and we would have needed to come from a metal-rich gas nebula, which would have come from the explosive death of some other star before then, and so on and so forth. So you see how we can trace our origins back to that, and before that, and before, and all the way back to those few quarks which we talked about in that cosmic soup in the beginning. Okay, so we can trace our origin back to exactly to all that. The universe continues to evolve. It's not static, it's changing, and every one of our body's atoms is traceable to the Big Bang and to the thermonuclear furnaces within high mass stars that exploded more than 5 billion years ago. Isn't that crazy? We are stardust brought to life, then empowered by the universe to figure itself out, and we have only just begun. Oh, this is so nice. This is Neil deGrasse Tyson's Astrophysics for People in a Hurry. We just finished chapter 1. That's so cool. We are stardust brought to life, then empowered by the universe to figure itself out, and we have only just begun. Okay, so I mean that will be that for tonight. Let me know if you have any questions, thoughts, last minute comments, etc. Oh, let me see. Hello, Arjun Sinha. Sometimes I can't see the comments. Hello again. I know, we just have the one moon. Because in Venus, the survival chance of any spaceship or rover is less than a week. Okay. Hello, Monster. Monster was here. I don't know. So I'm seeing the comments with a bit of a lag. So hopefully you guys are still here to say hi. Venus is like Earth. Aww. Why is Venus hotter than Mercury? Excuse me. What if we drop oh gosh. We're about to become Venus if we didn't colonize Mars till the end of. Aw, so okay. Thank you, Arjun, for all your comments. Really appreciate it. If you're interested in the planets discussions, we have a whole playlist on planets, on just planets, that you should definitely check out, okay? Is that a twister mat on the floor? Somebody's commenting on my. So, by the way, guys, I'm also on Instagram, Facebook, TikTok, everything that you can think of, really. Threads. My handle is OindreeB on all of them, as far as I can remember. OindreeBee, OindreeB. I post like about my travel and day-to-day life and lifestyle and all that stuff. Also some of the physics stuff on these other platforms as well. So I'm reading somebody's comment that they left me. We were eating on the floor on a mat, and they're asking, was that a twister mat on the floor? And I'm not sure like what that means, like what is a twister mat, but yeah, this mat like can be foldable or something. It can be folded up. There's no dining table where we were eating, so and we like it that way. We all sit on the floor and we eat. Aww. But yeah, if you are over on those platforms, feel free to also like, share, and subscribe over there. Or you can remain here, no worries. YouTube will be my main platform, probably always. So YouTube is the main platform where I push out most of the physics and kitty cat content, which the kitty cats have gone upstairs because it's too cool down here. YouTube is the main platform, okay? So where most of the physics stuff happens, the live streams happen, all the videos, shorts, clips, all that get posted. And then I also post some of that on Instagram, TikTok, Facebook, Threads. Is there anything else? Please do let me know. As well as also I infuse some of my travel content because I like traveling, regular Boston life, ocean, all that stuff is so some other things, if you're interested in those other things, are also on those other platforms. But feel free to stay or go there if you wish to also add those things and follow me there. I told you the handle, OindreeBee, same handle as YouTube, OindreeB. So I'm gonna, what is twister? I don't know. He's asking, was that a twister mat? I don't know. Oh, interesting. What is this? Okay. Well, Arjun and everybody, thank you so much for being here. And Arjun, please do check out the planets playlist. We have talked a lot about the planets in that playlist. We spent a number of lives talking about the planets constantly. So hopefully you find that to be interesting. Okay. Bye-bye, guys. Everybody, thank you so much for being here and have a good night. Snokomui, how are you? I see your comment on one of my videos. Says Buttercup. Hello, frankly being human. It was just the last comment that I was reading. How are you doing, frankly? There's also a Jessie in my comments that I would like to thank on this live, because whoever Jessie is has been leaving a lot of interesting comments. Frankly is saying, can I be friends with you? Who are you, frankly? And sure. I feel like a lot of my regular people are missing on the lives, but that's okay. Hopefully you see this later on. If you do, please do like, share, and subscribe, and comment on the video. And thank you. That will tell me that you saw it. Man, oh man. I'm waiting. I'm waiting for something and it's not happening. I mean, can I DM you and expect a reply? Yes, you can DM me on Instagram. Some people get replies. Yeah. I mean, it may take me a moment to realize that I got a DM because it goes into like message requests or something, but you can definitely DM me on Instagram. And I will probably get back to you. It might just take a little time, but generally I get to it. Okay? I think my Facebook message requests are less checked than my Instagram message requests, just so you know. I'm more on Instagram than I'm on Facebook. But I do have Facebook, and I do get content pushed out to Facebook as well. Thank you for liking the live. Can we get 10 likes? Can we get 20 likes? Can we get 500,000 likes? Thank you so much. Thank you so much. Relevance. No, 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 no. I just love this music by Hans Zimmer. I do believe. La 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 la. Can you imagine if we were discussing this topic and I could play Hans Zimmer in the background, but I cannot because it is not illegal. No, 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 no. So I use it in my Instagram reels instead. So you should check out my reels. And can you please like my reels? That would be amazing if you're on Instagram. Okay, was the audio video everything good today? Okay. I just saw something kind of funny. My nose is very red. Oh. Oh God. Okay. Well, I have zoned out for long enough. Oh gosh. Of course. I want to start making content soon, so I thought of making friends with budding content creators. Go on a journey and share experiences. You should. Thank you so much. Please do. And you can also tag me on Instagram if you have like whichever platform you're on, whatever is your main one, you can tag me if you find me there. Find my handle there. Or if you want to do a collab or something. I am here for it. Okay, so thank you so much everybody for joining. Really appreciate it. It's been a quiet live, but if you see this later, please do like, share, subscribe, and comment. And that's how I'll know that you saw it and what your thoughts are. And in general, take care. Thank you so much. Enjoy the winter if you're in the northern hemisphere. Enjoy the summer if you're in the southern hemisphere. Welcome to all my continents, and good night and good morning to all my continents, including but not limited to North America, South America, Asia, Europe, Africa, Antarctica, Australia, New Zealand, Australasia, Oceania, or however you say that. Europe, I think I said that already. All the oceans, all the anaerobic organisms in there as well. And we've had a lot of fun discussing some very interesting topics today. So hopefully you enjoyed, and see you soon. See ya. Bye. Bye. Good night. Good night and sleep tight, okay? Bye bye.